Hello and welcome to this presentation on DirectX 11 programming. In this presentation we're just going to show you how to initialize the DirectX 11 drawing components, some of the major drawing components necessary for using DirectX 11. The actual drawing of specific objects will hold off until a later time. We'll start out with a program that we looked at previously. This is just a basic Windows program, and if we build and run this, you'll see that we just have a window creation and the basic message loop. So this is similar from last week's presentation where we just have the basic message going, basic window being drawn. It looks like there's something that's trying to be done here with a mouse move. We'll go ahead and take that out for now. In order to use some of the DirectX 11 library, we have to add some include files and library files. For this initialization part, we just need a couple of files to be added. The first one is we have to include this DirectX 11, D3D11. So in our header file, we'll just add D3D11. It's also common when you work with libraries that you may have to, during the compilation or build process, you may have to link with certain library files. And in this case, we have to link with d3d11.lib. So in order to do that, we go to the project properties and we go to the linkers section, and in input we add something to the additional dependencies here. And we add the d3d11.lib. If you don't do this step, the errors that you get will be linker errors, and they'll look a little bit different than what you're used to perhaps with C++ syntax errors. So this doesn't change anything, but just gives us access to the DirectX 11 libraries. The next step that we have to do is to initialize Direct3D11 devices, contexts, and what we call the swap chain. In our discussions previously, we had discussed double buffering, and that's essentially what the swap chain is. It's a swappable chain of two or more buffers, one that we typically render to while the other is being displayed to the user. And when we finish rendering, we swap those buffers. The user sees the new one that's updated, and we draw to the other one. Additionally, there's a couple other buffers that we create. One is referred to as the depth buffer. The depth buffer is what allows us to discern between things that are far away and things that are closer up. In this diagram, you notice there's several polygons. We have a purple one in the back, and a blue one, and a lighter blue one, and a yellow one. If we look at this grid of squares in the front as the screen of pixels, for this particular pixel that's yellow, you notice that we can potentially see the yellow polygon and the blue polygon and the purple polygon. Which one do we draw? Well, to us it's obvious we want to draw the one that's in the front. How do we implement that in a program? It turns out the way to do that is with what's called a depth buffer. So with a depth buffer, every time we generate a pixel for a location, we keep track of its depth, or how far away it is from the viewer, or how far away it is from the screen. And if we find a pixel that is closer, then we draw it. But if we're rendering, say, the purple polygon, and we've already rendered the blue polygon, well, the pixel from the purple polygon will be further away, so we discard it or don't render it. And this is the essence of how a depth buffer works. It allows us to render only things that are in the foreground, not things that are in the background. Another buffer that we may use sometime in the future, not immediately, but it's referred to as the stencil buffer, and this allows us for masking out part of the scene and creating shadows and some other effects. Another object we need is the viewport, and this tells DirectX information about our screen, specifically the width and height, and some other information as well. In order to get started and create these device and swap chain and so on, we need to define some variables. And we'll put these variables in our header file. And to be honest, there's a lot of code here that we, just like in Windows programming, there's a lot of code that we use, and we don't really need to memorize all of it or understand all of it. It's that type of code that you use and it runs once and gets initialized, and once you get it working, you rarely make any changes to it. And this is something similar occurring with this DirectX initialization. So the next step then is we have these initialization functions that we've seen before, where we initialize the program, this app class, and we initialize the main window. Let's create another one for initializing Direct3D. There'll be a variety of steps that we have to take in order to do this. So one of the first steps that we want to create, or one of the first steps we want to take, is to create this DirectX11 device. And most of our programs, I think this session is probably best to leave them running in debug mode, and if so, then we want to create a debug device which will output potential error messages to the output window of Visual Studio. So that can be useful in spotting potential problems when your program runs. If you actually build a game that you want to release, then you probably want to turn these debug features off, and it can improve performance somewhat. But for now, in our learning environment, it's probably best that we leave these debug features on. There's a function here called D3D11 create device, and a couple of parameters to look at. One is this device flags, where we're creating a debug device. The other is we're passing in this driver type hardware. And what this means is we want to use a DirectX11 device that takes advantage of the GPU hardware acceleration. We pass in the address of this Direct3D device pointer, as well as a variable here called feature level, and the address of this D3D device context. It turns out that these two, the device and the device context, these two pointers, object pointers, they'll be used quite a bit in our function calls for Direct3D. The function returns a handle to a result. Basically, it's a number that tells us if it passed or not, if it worked out okay. So we'll do a little bit of error checking. The first is if the device failed, we'll print out a message. The second is if we don't have the right feature level, and we can look up in the documentation what this means, but basically we want to make sure that our hardware device supports DirectX 11, and that's what this section of code does. The other thing that's optional is we can check on the multi-sample anti-aliasing quality level. So this is really somewhat of an optional step. It's not really critical, but it can be nice to know what the anti-aliasing quality level of our device is. So now we're ready to create the so-called swap chain. And there's several steps involved on this. So here's one of the first steps here is we create this, and this is not uncommon in DirectX programming, where you create a variable that is a structure that has a bunch of different parameters in it, and we call those a descriptor. So here's the DirectX graphics interface swap chain descriptor. It's just a local variable, so we just give it a short name, SD. And it has a bunch of parameters in here, properties or characteristics of the swap chain that we want to create. And again, a lot of this you won't change very much, so it's not really critical that you memorize or understand exactly how everything's working, but we'll look at a few things that we should be able to understand and follow. The first two are pretty obvious, the screen width and the screen height. That makes sense. We can look up in the documentation about the refresh rates, especially if it fails, we may need to do something different on your particular hardware if your hardware doesn't support a certain refresh rate. The other is the format. So the format here is that we're going to use an RGB 8-bit format for the swap chain. So that gives us 256 different levels of red, green, blue, and alpha channel for transparency. Specify that we want to use this, want to have a buffer that can be used as a render target so we can draw to it. We want one of those render targets, and we specify that the output window is the handle to the window that we created. So if you recall, previously we created a Windows program and it had a window handle, and we have to tell it which output window we want to draw to. And so this brings up the idea that if you wanted to create a program that had 2 or more windows and you wanted to draw to each of those, then you could create 2 or more swap chains and render maybe a top view to one window and a front view to another window. And that's certainly possible. So the next thing, in order to actually create this swap chain, we have to query for some devices. And this syntax is kind of odd, I guess, but so we query for this DirectX graphics interface device, and then we query for an adapter, and we query for a factory which allows us to construct certain things, and then we call this create swap chain. Pass in the descriptor for the swap chain and pass in the address of the swap chain pointer. And this is a fairly important step that we do. The next step is when we query these interfaces, they are resources that we asked for, and we only needed them to create the swap chain, so now we can release them. And you can either call they all have a release function, so you can just call it like that. Or I find it useful to create this release com function, and it might look something like this. I usually put it in a header file. Sometimes it's done as a function, sometimes it's done as a macro. So here it's done as a macro using a pound define. So everywhere the preprocessor during the build steps sees this release com, it'll substitute this code here, which means basically asks that if it's pointing to something that's not null, call its release method and then set it to null. And this will prevent us from trying to release something twice or trying to release something that has not been allocated properly. So if you try to release something that's null, you're going to get a runtime error. So this actually creates the swap chain part. The last part of this function is we want to call this on resize. So notice up here we created the width and height with, or the swap chain with a certain width and height, but we also allowed for the window to be resized so the user can change its size. So we want to call this on resize function here, and also if the user changes the size of it, we want to call the on resize because we need a different size swap chain, a different size width and height for our back buffer and render targets and so on. So the order of these methods in the class declaration isn't critical. I like to sometimes put them in the order in which they're called. So maybe the next one might be run or might be on resize. Let's do the on resize next. Right now the on resize doesn't have any code in it. What should we do in the on resize function? The first thing that we want to do is to assert, call this assertion function. We want to make sure that the swap chain and the device context are valid pointers. And so this assertion will fail and we'll get an error message if they're not valid pointers. This should all work out okay. The next thing we want to do is to release the render target view, the depth buffer, the depth buffer view and the depth buffer. And the reason we want to release them is because we have to make them again because the window is resizing. So here we are resizing one of our buffers, and we're resizing it to the screen width and screen height that either got set in the initialization process or got changed due to a user resizing the window. Here we're asking for a pointer to the back buffer, and then from that back buffer we're creating that render target view, which we need. That's what we're actually going to draw into. And once we've got this render target view, then we can release the back buffer. The next step is to create the depth and stencil buffers that we talked about. And to start off with, we create a descriptor for the depth and stencil buffers. And because these are just essentially like images, we use the texture 2D descriptor structure for setting their properties or asking for certain properties. Once again, we see the screen width and screen height. MIP levels, I don't know if you're familiar with MIP mapping, but in texture mapping, you can actually have several levels of textures to look up in, almost like a 3D texture. Here the format, we're setting the format for the stencil and depth buffer, and the first one, the D24, means that we're going to get 24 bits used for the depth buffer, and we usually want a fairly high resolution depth buffer so that we can distinguish between two, say, planes or two polygons that might be intersecting each other. So we usually want a fairly high resolution. 24 bits is common. For the stencil buffer, because we're just using it as a mask, whether to draw a pixel or not, we can get by with just 8 bits here. And again, many of these other flags we can look them up if we need to, but it's something that we rarely change, so we don't worry about them too much right now. And then we call the functions through the Direct3D device to actually create the depth buffer and create the depth view of the depth buffer. Once we've done that, then we want to set that depth view as the render target for our render target view. So we're going to draw through the render target view, and our drawing will use the view of the depth buffer. So we're setting these as our render targets. And finally, on the resize, we want to reset the viewport. And so within a window, it's possible to, you don't have to draw within the entire window, but you may want to use some of the window for buttons or other GUI controls. But here we're saying that we're going to draw in the viewport starting at 0, 0, and we're going to go to screen width and screen height, and then our minimum maximum depth is going to be 0, 1. And again, these 0, 0 width and height are kind of critical. The 0, 1 we don't really change very much, and then we set the viewport on this D3D device context. So this takes care of what happens when we resize, either after an initialization or after the user changes the size of the window. And again, there's a lot of code. You can go through the documentation for all of it, but it's really only bits and pieces of it that you need to really focus on, because most of it won't change. So the next step would be the run method. And if you recall, we kind of left a comment here that says we'll add some game stuff later, or some rendering stuff later. Well, now it's later. And so we're going to add a couple of function calls here. One we're going to call our update function, the other we'll call our render function. And notice I've got a value here, 0.1. Later on we're going to substitute an actual time. We don't really need to do a whole lot in the update function right now, but in the future when we update the scene, we want to pass in the frame time, maybe to do physics calculation or motion or animations or something like that. So this is just a placeholder for the frame time, and it'll actually be much smaller than that. So now we're ready to put in our update and render functions. So those are the prototypes for the update and render functions. Just going to move this shutdown after run, I guess, after on resize. We'll put it here. So again, on our update, for now, we don't really need to do anything yet. I don't think. In the render, we obviously have some things that we want to do. So in the render function, again, we're going to assert that the device context and the swap chain are valid pointers. We're going to declare a color of floats. So this is a 4D color for RGBA. We're going to clear essentially the back buffer, so we clear the render target view to that color. And then we're going to clear the depth and the stencil buffers. And the depth buffer you clear to 1.0. So what happens is the actual depth of our scene in different transformations in the viewing and projection transformation will get scaled to 0 to 1. So the furthest thing away after the scaling will be 1. And so we're going to clear the back buffer to be 1, so we're essentially setting it to the furthest possible thing away, and we're clearing the stencil buffer to 0. We're not really using that right now, so it's not critical for us. And then we're presenting, so-called presenting the swap chain. That just swaps the buffers. It says, okay, show what's in the back buffer right now. And I believe the last thing that we need to do is clean up these pointers that we've created when our program shuts down. So a lot of these interfaces that we've used, like the device and the device context and the swap chain, these are object interfaces that are allocated and take up resources, and it's important to deallocate them when we no longer need them. So if we go down to the shutdown, we're going to release, as we've seen before, the depth view, the render target view, the depth buffer, swap chain, and so on. And we're going to compile it here. It looks like it's going to compile okay. Let's see if it runs okay. If we forgot anything. Okay, so we've got a problem where an exception was thrown here because the device context wasn't valid. And we've got some diagnostic output here. And it turns out that we forgot something rather important, and that is when the application gets sized either for the first time or gets resized, we didn't call our resize function. So what we do in this case is when we get our size message and the device is valid, we want to call our resize function. Let's see if that's what caused the problem. Well, we still have this exception problem here. So it looks like there's another key thing that we forgot to do, and that is we went to all this trouble to define this init direct3d, but we never called it. We never invoked it anywhere. There's different places you could put that. One is right here. When we initialize the application, after we initialize the Windows window, then we can call the initialization for the direct3d. So now we get a window, and as you recall, the color that we specified when we render the RGB components of that color were 0, 0, 0, which is all black. If we change one of those color components, so in this case I changed it to 001 RGB, so that gives the blue component a 1, so we get a blue background. And something interesting you may want to try, we'll add some time capability in here, and you can just put in a static count variable, count the number of frames. Something interesting you may want to try is to just change the output or the background color every frame, or change it with time. So you can have it fade in and fade out between different colors. You can have it flash on and off. Variety of different effects you could do. Be a good challenge, good extra practice. So we've seen that how we've made the swap chain and the rendering. And this is a basic image of how double buffering works. We have the screen or the primary service that the user is looking at. The program is rendering graphics to the back buffer. Sometimes they call it a blit or a copy. In our case, it's presenting the back buffer or flipping the swap chain. And now the user gets to see what was drawn. We clear the back buffer and we start drawing the next frame. We talked about the importance of freeing up or destroying the objects. It turns out that we're actually, instead of really restoring them, we're actually recycling them because they're memory. We're freeing up that memory, and that memory goes back to the pool of available memory that our program can use. So it's important to free up, or we call it free up, sometimes destroy or release. It's actually being recycled and it can be used later. What happens if you forget to do this? In most cases, if you forget to do this, your program won't shut down gracefully. You'll get some error messages when your program shuts down. In some cases, for example, in the case of the resize, if you don't free up the resources properly, then every time a resize is done, you may have an object in memory that's not released. And then the next time a resize is done, you may have 2 or more objects in memory that are not released. And then the next time, 3 objects. And if this is done very frequently, especially if this is done in a rendering loop, if you're allocating objects and then not releasing them properly, and then this is done in a loop that occurs over and over again, you can have a serious problem that we refer to as a memory leak. And so a memory leak occurs when essentially the result of it is the available memory to your program is being reduced over and over because you're allocating something and not releasing it properly. So it's almost as if the available memory is leaking from your program. That's not what's really happening. What's really happening is the memory is being allocated for something and then never being released, and then you no longer have access to it. One way to detect a memory leak is by using your Windows Task Manager. So if you open up your Windows Task Manager and start looking at the tasks within your program, one of the columns here shows the memory that your program is using. So let's see if we can find ours. If I go over here to our program and run it, so here's our program that's running, and we may not realize it now, but this back buffer is being drawn over and over again very fast, and we'll see just how fast in a minute. If we look at the task manager and try to find the task for this, it'll be the one that's using up a good bit of CPU here. This is it, our week 1 Windows program. We didn't change the name of the project, so the executable got the same name. And you see that it's using about, what, 6.5 megabytes of memory. The other thing that you notice is it's fairly steady. The amount of memory is not increasing or decreasing. Now, if I resize the window, I would expect the amount of memory to change because my buffers being resized or changing. And we see that the amount of memory did in fact change, although it's not being redrawn properly. That's interesting. It's not redrawing to a blue color like we expected. Let's see if we can figure that out. So it turns out that for whatever reason, I'm not familiar with this Windows message. I'm not sure exactly where this came from, but this window message here, enter size move, this code really doesn't do much, and it was causing the window not to start rendering again after it was resized. I'm not exactly sure why that is, but when I took it out, now you see that we've got a window and it seems to be resizing properly. So what we wanted to talk about was possible memory leaks and how you might be able to detect them or be suspicious of a program that might have a memory leak. And one thing you can do is you look in the task manager and find your program running in the task manager, and you see that it's taking, in this case it's about 7.8 megabytes of memory, something like that. And when you resize it, you might expect it to change the amount of memory that it's using, and of course it's using more. And if you make it smaller, you might expect it to start using a little bit less, and in this case it didn't change. One thing you do want to look for though is if the program is running and this memory size and the program isn't doing much different, so the program's basically doing the same thing over and over again, drawing the same scene over and over again or something, and this memory amount is increasing, that's something you might want to be concerned about for a potential memory leak. And they can be very difficult to find. It's difficult to debug a memory leak by using typical debugging techniques. One technique that I try to use to spot memory leaks is simply just commenting out sections of code. I say, okay, the memory was increasing. I commented out this section of code. Now the memory is pretty steady. So that leads me to believe that the section that I commented out may be the area that contains the memory leak. That's not the most efficient way of finding problems, but it can be a useful technique. All right, one last thing we want to do is look at some timing. I'm curious to know how long is it taking in between frames, or maybe what the frame rate of our program is. And often we need to know the time for each frame in order to do some type of updates, like physics updates or animation updates or so on. There's different ways of looking at time, different ways of getting time within a programming environment. One thing that we need is a fairly high resolution timer, because our frame rates with these modern powerful GPUs can be fairly high. We can get frame rates in the hundreds or even in the thousands for simple scenes. And so you need a timer that has a fairly high degree of accuracy. One that's commonly used is what they refer to as the Windows performance counter. So your processor, your CPU, has a counter on it, and it increments pretty much at the frequency of your processor. And you can get that counter, and you can get that counter frequency, and you do some math, and you get the amount of time in seconds. Another possibility is the C++11 standard that came out in 2011 introduced a chrono library. Some of the syntax is a little odd, but you can use that to get time as well. What I've done is created a class for a timer using the performance counter. And I will show you that. So I'm going to add this timer.h to my program. It shows up here. And so I've been using this C timer class for a while now, for some years now, and it seems to work fairly well. You need to include windows.h. I'm not sure that I really need string. Sometimes I convert some timer values to string, but when you work with this performance counter, and you can look up more about this at MSDN, the performance counters. There's two key functions that you want to use, and I guess there's a lot more, but the ones that I use are, well, they don't seem to be in here. Well, the ones that I use are query performance counter. I guess we could just look that up directly. So here is query performance counter, and it returns an odd type. It returns a type that they've defined, a pointer to a large integer. So that's kind of an odd thing. I believe it's a 64-bit value. So we declare in the class a frame count to keep track of the number of frames that have been rendered, a large integer to keep track of different times, and we want to know the frequency of the timer, and that'll vary per CPU. So everybody's CPU has a slightly different frequency, so this will vary per CPU. We want to have a start and an end time. Maybe we want to keep track of how long something takes. And then I also have this last frame start. So every time I finish rendering a frame, I'll let the timer know so it can update this last frame start. So sometimes we want to know the difference between the end and the start time to see how long something took. Sometimes we want to know the difference between the end and the last frame start so that we know what the frame time was for things like physics updates. In the constructor, we set the frame count to 0, and the performance, we queried for the performance frequency. We can reset, which sets the frame count to 0 and sets both the timer start and the last frame start to the current value of the performance counter. We can call next frame, which just updates the frame count. and I don't think this is right. The get frame time, it says it's going to get the time since the last next frame, but and it gets the end time and subtracts the last frame time, but that wasn't queried for in next frame. So I think in next frame we need to, looks like there's a bug here, we need to also get the timer value since the last frame. And notice this syntax for computing the results is a little bit odd. I take the timer end and the quad part, which allows us to access it as a numeric and do operations on it. So I essentially take the timer end and subtract the time since the last frame began. And all this does is give me the number of counts in the performance counter. That doesn't actually give me a time. To convert this to a time, I have to divide it by the frequency of the performance counter. And frequency is in hertz, and the units for hertz are 1 over seconds. So if you divide by 1 over seconds, you get seconds. So frequency is in ticks per second, and the numerator here are the number of ticks or the number of counts that occurred. So you divide counts by counts per second, you end up with seconds. So this is the actual time. This is the actual time that we get. Oh, okay. So here is where the last frame start's going to be set to timer end. So, so we don't need that there. So maybe the first frame that we ask the time for won't be terribly accurate. That's a possibility. But after that, it should be accurate, because what we're doing is setting the start of the last frame time to the end of the current frame time. So that makes sense. And then we return the result of this time. Get elapsed time, this just gets us the time between the end and the start. So if you want to measure how long a load or initialization or how long some algorithm takes, this would be a useful result. And these are in seconds. The results of this is in seconds because the frequency is in ticks per second or counts per second. And then get frame rate. So when we do get frame rate, the calculations are a little bit different because we want seconds in the denominator, we want frames per second. So we take the frame count, and when we compute the time, it's n minus start, but we put that in the denominator underneath the frequency so that we get frames per second. So this is going to be frames, this is counter ticks per second, this is counter ticks, so counter ticks per second divided by counter ticks is just per second, so this ends up being frames per second in terms of units. So now in our application we can declare or include I should probably not this. I should put this in our header file. Our timer. And then somewhere in the variables of our class we can declare a timer. And if you need more than one, you can declare 2 or 3 of them, just give them different names. When we do an initialization, we may want to reset the timer, maybe after we initialize Direct3D. And then we can actually call next frame in here. And so let's see if we can put the frame time in the window. As you recall, in the discussions we talked about using swprintf to print out a string, and our strings now are, they're W character types, right? So we declare an array of this wide character type to be of a constant size. Make sure it's big enough for whatever message you're going to print out. And we can pass in the size to make it safe so it doesn't overflow that buffer. And then we have some kind of format string, so we can say frame time, or actually we can use our app name. And remember that we have to convert this format string to a wide character or something like that. And then we want to use our timer so here we just declared an array of this wide character type since we're using Unicode character set. Here we're using the swprintf to create a formatted string that has a placeholder for our application name and a placeholder for the time that each frame takes in seconds. So I've got 4 decimal places of accuracy. I expect this to run pretty fast per frame, I think. Oh, I forgot to do something with this string. How do we get this string on the output? To put it in our title bar, we have to call setWindowText. And pass in our window handle and pass in our message string. And what you can see is that our frame time, you can barely see it. It's actually taking up, it looks like that might be a 3, 4, 5, 10 thousandths of a second, so it's pretty fast, right? And gamers generally prefer frame rate. So instead of calling the get frame time, we can call get frames per second. And you see it's going pretty fast here. It's at 17,000 frames per second and still increasing. I think it decreased a little bit when I moved it from one screen to the next or resized it. So it's 1,800 frames per second, and that makes sense that it should be ridiculously fast because we're not really drawing anything. We're just clearing the back buffer and showing it. So this should be a really fast operation. We'll see this frame rate come down in future work as we add more work for our GPU to do, more vertices to be drawn and pixels to be filled in and so on. So that ends this presentation on Direct3D initialization. Let me know if you have any questions about it, and we'll see you in the discussions.